We finished section 8 going over some of the special cases that involve absolute value with equations and inequalities. We didn't look at any of the special cases up to this point, but we'll try to cover as many of them as we can now. We'll start with equations. Now, the absolute value of an expression equals a number. What we've been doing is we've been setting the expression inside equal to the number or its opposite. But notice this time it's not a positive number. The absolute value is completely by itself on one side, and there's a negative number on the other side. Well, what number can you plug in for x that when you do the arithmetic and then take the absolute value is going to be equal to a negative number? Well, there is no number. This is the empty set. This is a special case. This cannot equal a -6. It can't be a negative number. Now, if there's a -3 out here or something that you have to divide both sides by first, then that becomes a positive number and you'll work it and you'll get an answer. So be on the lookout for that. Make sure the absolute value is isolated. Here's another special case. The absolute value of some expression, I just used 2x minus 3, greater than or equal to a negative number. Well, absolute value, again, it's already all by itself on one side, is always non-negative. So it's going to be greater than or equal to a negative number no matter what we plug in for x. So this is an identity. It's going to be true for all values. On the other hand, the absolute value of 2x minus 3 is less than or equal to -6, a negative number. Well, that can't happen. You can't have a non-negative number less than or equal to a negative number. So again, the absolute value is all by itself. There's no -3 out in front that you'd have to divide by first. This case, this is not going to be able to happen. This is a contradiction and there is no solution. Now I have 4 examples that are similar to what I have here, a little simple here, and there's a couple of extra things I want to point out. It says solve the inequality, write the solution set in interval notation when appropriate. Well, this is a little bit like the one I just did here. I have the absolute value already by itself less than a negative number. That can't happen. Can't be less than a negative number. On the other hand, it can be greater than a negative number, as this example here showed. The absolute value already all by itself, greater than -2, this can happen. And in fact, this is an identity. No matter what I plug in, because I'm taking the absolute value, it's going to be non-negative. It's going to be greater than -2. So negative infinity to infinity. It's an identity. This is a little different because I have a 0 here. I don't have a negative number. I don't have a positive number, but I have a 0 here. So I look at this and I say, okay, when is the absolute value of x plus 1 less than or equal to 0? Where it's never less than 0. That's kind of what we were talking about here. It can't be negative, but it can equal 0. X plus 1 can equal 0, which means x can be -1. So I have just that single number. Over here, when can this be greater than 0? Well, it can be greater than 0 for pretty much any number we plug in because we know that the absolute value is non-negative. We do have to exclude one value because we can't have x plus 1 equal to 0. We have to exclude the -1 because if -1's in here, we get 0 greater than 0. That's not true. So it's every number except -1, which I'm going to write as negative infinity to -1 parenthesis from -1 to infinity, and then I'm going to use the union symbol in there to represent all numbers except for -1. I finished this section with a simple example of how to do an application problem, a story problem, that we'll use in inequality. And it says for a recent year, the monthly snowfall in inches in Chicago for November, December, January, and February was 2, 8.4, 11.2, and 7.9. Remember, this is in inches, respectively. How much snow would be necessary in March for Chicago to exceed its monthly average snowfall of 7.28 inches for those 5 months? Well, let's let x be the amount of snowfall in inches for March. Since we are looking at an average here, I'm going to add up all the values. I'm going to add up these 4 months, the 2, the 8.4, the 11.2, and the 7.9. That's for those 4 months. And then also the 5th month, which I've called x. And I'm going to divide this by 5. That's how you find an average. And we want this to exceed. We want it to be greater than its monthly average of 7.28. So that's my inequality that I'm going to use to solve this problem. Now I'm going to add all of these numbers up here. Let's see if I can do this in my head. 7.9, that'd be 18, 19.1, 19.5, 27.5, 29.5 plus x divided by 5 is greater than 7.28. I'm going to multiply both sides by 5, and because I'm, again, starting to run out of space here, I'm going to have to write a little smaller than I would choose to. So 5 times 29.5 plus x over 5 is greater than 5 times 7.28. Now because I'm multiplying by a positive number, I do not need to reverse the order, and I'm going to bring it over here. So I have 29.5 plus x is greater than, now this, I have to multiply this out. This is going to be, see, 0 carry 4, 4 carry 1, looks like 36.40 if I didn't mess up too badly. I'm going to solve for x. I'm going to subtract, here let me get on this side, I'm going to subtract 29.5 from both sides. And since this only has one decimal place and this has two decimal places but the end's a 0, I'll just leave it as 36.4 minus 29.5 just for convenience. And I have x is greater than, what would that be, 6.9. So, how much snow would be necessary in March? It would have to be greater than 6.9. So Chicago will need more than 6.9 inches of snowfall in March to exceed its average, to exceed the average. And that's a pretty straightforward type of problem. Now there was a lot of work in this first chapter on the prerequisites for pre-calculus, and I did numerous examples over the many videos. However, I can't do an example of every single type, and so I would like for you to make sure that you've been practicing these problems. If you feel like you're overwhelmed by the information in these first 8 sections of this prerequisite chapter, then perhaps you've been placed incorrectly into the class, because you should have a pretty good feel for this before you're ready to go on to the newer material. But at the same time, you've worked hard, so why don't you give yourself a hand? Well, that's not giving yourself a hand. That's giving yourself a fax machine. Let's give yourself a hand. There, we got it. And keep working hard and practice, practice, practice.